Okay, so this is the regression for univariate variable. Now let's look at the regression for multivariate variable. Okay, see, this is multivariate regression. Multivariate regression means this. See, we no longer have one-dimensional data. Now we have two-dimensional data. We have x1, x2, up to xt. But this is simply a linear model, but we have W0 plus W1 times x1 plus W2 times x2 up to WD times xt plus epsilon. We start with this one, okay? So suppose we use this model, okay? We use this model. And of course, the square error is defined as this. Now you know, either from the perspective of maximum likelihood estimation or from the square error between the estimated output and the given output. Okay, so this is supposed to be the error, and you sum every error. This is okay. So in order to minimize, we want to minimize this, right? If we want to minimize this square error, then we have to take partial derivative of this square error with respect to W0, W1 up to WD. So we take partial derivative of this. We do exactly the same as what we have done for univariate variable. So we will have the equation like this. Okay? Then we could arrange those d plus 1 equation. We totally have d plus 1 equation because we have d plus 1 unknown, W0, W1 up to WD. So d plus 1 unknowns, we use d plus 1 equations to solve those unknowns. So we arrange our x or our d like this. 1, x1, x1, x1. Oh, yeah. We have x1 up to xt, and wait a minute. Yeah. For x1, we totally have n data, so we arrange the n data like this. For x2, x1 squared, x1 third. Oh, no. All right. Yeah. Yeah, x1 up to xn. Take this as an example. All right. Okay, so see, we totally have, here we have 1800 data. So capital N is 1800. So x1, over 1800. x2, over 1800. x3, over 1800. So this x is like this. x1 up to 1800, x2 up to 1800, xt up to 1800, that is called x. W is this, you know, W0, W up to WD, and we arrange this so we could have x transpose x times W equal to x transpose R. The y term here is x transpose R, and the A term here is x transpose x. So W is equal to this. So you simply arrange your x this way, you can calculate W by this equation. That's it. Do you understand? So x1 up to xn is, so we have x1 up to xn, x2 up to xn, xt up to xn. The formula is this. x1 up to xn, x2 up to xn. So all this is a, so totally we have x is a 1800 by 10 matrix, that is x, okay? So by arranging your x this way, then you are able to calculate your estimated parameter, vector W, defined as this equation here. So again, this is, we are not doing the matrix inverse for a very large matrix. X has a large number of rows, right? And x is a n by d matrix. So n is large, but don't worry. D usually is not that large. D, for example, here in my data, D is only 10. N is large. But we are going to calculate this. So this is n by d, and x transpose is d by n, right? And this is n by d. So totally, this is d by d. So this is simply 10 by 10 matrix, square matrix. We do this inverse. That is reasonable, okay? If we are going to do the inverse for 1800 by 1800 matrix, that is almost impossible. Okay, so this is okay. So as long as we have calculated this, then we will be able to do this. Now, similar to this linear regression, we could suppose we are going to use a model. See, this is a very nonlinear model, right? You see, W0 plus W1 times xt, W2 times cosine xt times x2t, x1t times x2t, W3 times exponential minus 2 x3 squared. Sorry, this is not correct. x3t squared, this is not correct. x3t squared, okay? And x6, and this, sine this. So this is a nonlinear polynomial, but the parameter is linear. There's a name. Let me see. Okay, you see, linear combination of some basis function. Those are basis function. This one, this one, this one, this one. Those basis functions are not linear, but they are arranged in a linear combination form. what is linear combination form? We have W0 plus W1 times this basis function plus W2 times this nonlinear basis function plus W3 times this nonlinear basis function, something like this. So this, we could apply this kind of linear regression model to solve the nonlinear problem. The assumption is that the basis function can be nonlinear, but they have to be in linear combination. If we can do that, we call this W1. We call this Z1. We call this Z2. We call this Z3. And we call this Z4. So, for this, I want to give you the data like this. So I will give you this, and then I'll give you y. So I have some x here, and I have y here. But I want you to estimate the parameter like this. Okay, so this is the parameter. We want to calculate W0, W1, W2, W3, W4. Well, I only want you to calculate W0 to W4, but those parameters are in a very nonlinear function like this, nonlinear polynomial. They are in, the basis function is this. So how to do that? You are given this, and this this A is like this. This is I will give you x1, x9 up to x9 and A. Then A is generated this way. So how do I do this? Okay. So the way, so we have, I will give you this. The way we do this is we call this basis function z1t is probably x1t, but z2t here is equal to cosine z3t here is I'm sorry, I neglect some form, so I don't use x5 or I don't use x6, 7, 8. So I just want to explain how we do this. So the third basis function is this. Okay, so those are the so-called basis function. Okay, so A now can be written as W0 plus W1, Z1 plus W2, Z2 plus W3, Z3 plus W4, Z4. So the AT is given like this for t equal to 1 to capital N. So I give you x1t up to x9t and AT. You have to transform this data into this Z1, Z2, Z3, Z4, and A. So this. And Z1, Z2, Z3, Z4 are calculated based on this. So you are transforming this nonlinear polynomial to a linear polynomial like this. So this is equal to W0 plus W1, Z1, plus W2, Z2t, plus W3, Z3t. If we can transform the AT to be this, that is much, much easier. Then you can solve this problem like this. Except that this is no longer x, it's z. That's it. All right? I will give you this kind of problem. You have to do it by yourself. Practice this. All right? So no matter what kind of nonlinear function you are going to have, you don't have to worry. You probably need to use trial and error to guess or know the characteristics of this nonlinear function. Then you can guess your model like this, and you can use this linear regression approach to calculate those W0, W1, W2, up to W4. That will be easy. So this is another way for us to model the nonlinear system. All right? And then, so this is easy, right? Now you understand this, because this is a simple multivariate. This is a simple multivariate regression model that is easy to calculate. Okay, so I've covered the most important parts. Now I will give you some detailed explanation, especially some important concept. Okay, so far, any question? Any questions so far? We'll cover. So I think that by next Monday I will be able to finish chapter 4 and chapter 5. So you will have very clear concepts about classification, regression, normal distribution, parametric model, and okay? Okay, now let's come back to see those detail things. Okay, we start with this. The mean square error, the regression error is that is the square error. Okay, we sum everything together. But for mean square error means you take the square. This is if we have a model that is denoted as d of x, okay, because this model used the data x, d of x, to estimate the parameter theta, okay? So you take then the error will be d of x minus theta, right? Take the square, and then you take the expectation. This E is expectation. It's not error, it's expectation. This is called the mean square error. Mean square error, this like this. So the definition of unbiased estimator is this. We define the bias. Bias is we use d of x to estimate theta. So the expectation of d of x, we hope that expectation of d of x should be as close to the real parameter theta as possible. Okay? So if our estimator is good, if d of x is good, then the expectation of d of x will be exactly equal to theta. Then we call this, this is called bias. If the bias is 0, then our D is called unbiased estimator. Okay? This is the definition of unbiased. Oh, by the way, the following I'm talking about, the following property I'm talking about is also satisfied for a multivariate variable. Okay? Because if we use univariate variable to explain those important properties, that would be easier to be understand. Okay, so this is, so in order to check whether our estimator is unbiased estimator or not, let's see. Do you remember the mean? The mean is defined, that our estimator to calculate the mean is defined this, right? Summation t equal to 1 to n, xt divided by capital N. We take the expectation. And according to the property theory, the constant can be taken out of the expectation. So this is equal to 1 over n times this. And then, do you know what x, for random, now x, don't forget x is a random variable. Expectation of xt, what is this? It's mean, right? It's the mean of this random process. So expectation of xt is mean, and we sum everything. If this is mean, we totally have n mean, so n times mu. So that is mu. So expectation of n, which is defined as this, is exactly equal to the original mean, which is mean, statistically. This is the statistical mean. This is estimated mean. So our estimated mean, or calculated mean, is exactly equal to statistical mean. What does this mean? It means that this approach is unbiased, right? If this is 0, then E of d of x is equal to theta. Theta now is mu. This is the calculation the model we are going to use. This is our d of x, and this is our parameter theta. So E of n is equal to mu. So we know that this approach is unbiased. Okay? Now let's see the variance of mean. The variance of mean, mean is this, right? The calculated mean is this. And the variance, according to the probability theory, the constant inside of this variance is equal to square of this constant times the variance. So you take this out of this variance, it will become n squared, 1, and so we have this. And then variance of xt, we know that this is sigma squared. And we totally have t equal to 1 to n, so we have n times sigma squared. Divided by sigma squared is sigma squared divided by n, which so what does this mean? It means that this sigma square is the variance of this random variable xt. This approach, this estimator, the variance of this estimator, actually equal to sigma squared divided by n. So this tells us that this approach, if we increase the number of data we use, n, the variance of this approach could be very, very small, because if n is very large, this value is very, very small. So very, very small, what does this mean? It means that the variance of this approach can be a very small value, almost equal to 0. So if this almost equal to 0, it means that it will not vary too much. So if we use this approach to calculate the mean, it will not, if we increase the number of n, the variance will be very, very small. So every time we use this approach to calculate the mean, it will not, well, of course, it will be, this time I use the data here, I use this approach to calculate the data. Next time I do it again. Every time I use this data to calculate the mean, the mean might be different a little bit, but it will not be too much different because the variance is very small. The variance of this approach is very small. As long as we put n very, very large, this is very small, so it will not jump too far away from the real value. This is what I mean, variance of this. And similarly, we know this is how we calculate s squared, right? S squared is equal to this. If you extend this term, the square term here, we have xt squared, 2m times this, plus, because we are summating, this is the constant, so summation t equal to 1 to m squared, you have total m times m squared divided by n. So this is Yeah, so you have this term here, right? And this is m squared. And let me see, where is this? Where is this term? Oh, this is n, right? Summation t equal to 1 to n xt. This is n. This is divided by n. This is n. m times 2m, this minus 2m squared. And you have plus m squared. So totally you have minus m squared. You have this thing here. So you have this. So if you extend this s squared, this is what you have here. So expectation of s squared is the same as expectation of this minus expectation of m squared, right? And then from the probability theory, expectation of x squared is equal to sigma squared plus mu squared, okay? Or sigma squared is equal to expectation of x squared minus mu squared. So this is see, variance of x is equal to expectation of x squared minus expectation minus m squared or mu squared. So e squared is equal to variance of x, which is sigma squared plus this. This is mu squared, right? So this is this. Why do we want to use this? Because if you look at this term here, this term, this is summation t to the, we have x1 plus x2 plus up to xn squared. So this term, if we have x1 up to xn, x1 plus x2 up to plus xn squared, we have, if we extend this square term, we have this plus this. The extension of this square term is this and this, right? Square term, purely square term, and t equal to 1 to n, t1 equal to 1 to n, t2 equal to 1 to n, but t2 not equal to t1. Because t2 equal to t1, we have this term. So we have this. And then you take the expectation, you have this plus this and this, right? Because they are xt1 and xt2 are independent, so expectation of xt1 and xt2 is equal to expectation xt1 times expectation t2, as long as xt1 and xt2 are independent. So we will have this. So this term, now we know this is sigma squared plus mu squared. We have this. And total n of them. So n times this. And this term is equal to, this is mu, and this is also mu. So mu times mu is squared, mu squared, but we have n times n minus 1 terms. So n times n minus 1 mu squared, we have this. And then divided by n squared, so you will have n mu squared is cancelled with this n times minus n times mu squared. So we will have n sigma squared plus n squared times mu squared. You have this. So totally we have this. Okay? So expectation of m squared is equal to this. Why do we want to calculate m squared? Because we want to calculate this term. Okay? And then expectation of s squared, we go back to this term here. This is sigma squared plus mu squared, right? So we have sigma squared plus mu squared times n, this term, summation, so we have n times sigma squared plus mu squared of this term, and this term here is what we have calculated here. Expectation of m squared. Expectation of m squared times n is equal to this times n, right? So this times n. So then we do some calculation. We will have n minus 1 divided by n times sigma squared. So you will see the expectation of x squared, which is the calculation here, is equal to n minus 1 divided by n times sigma squared. Unfortunately, this is not exactly equal to sigma squared. We have n minus 1 divided by n. So this approach is not an unbiased estimator. In other words, if we use this approach to calculate the variance, it is not an unbiased estimator. It is a biased estimator because expectation of s squared is equal to n minus 1 divided by n. Not exactly equal to 1, but almost equal to 1. So s squared is a biased estimator, but we know that the expectation of s squared almost equal to s squared as long as n is large. So if n is large, this estimator is almost an unbiased estimator. This is what we want to see. Okay. All right. So you know why I jump over chapter 4 and 5, because those are the important property, but not directly related to our exam. But this is to make you have a clear concept. Okay. Once we know bias and variance, now let's take a look at this is a very famous theory. Okay. Let's take a mean square error, which is this. D, don't forget, D is the estimator, right? Theta is the parameter you want to estimate. You extend not extend. D minus theta, you subtract expectation of D and plus expectation of D. So you have done nothing, right? You minus this and add something here and minus theta here. So it's the same, this is still the same as this. But if you do this, you extend this square term, you will have the square D minus expectation of D square plus 2 times D minus ED times ED minus theta, which is this term. And then you have ED minus theta square. This is the second term. And then you take the expectation. So you have this expectation and this expectation and this expectation. Now, so this is the same here. This expectation is, for this expectation, we have already calculated this expectation. So this expectation is a constant. So take the expectation of this constant, it's still a constant. So theta is a constant. Theta is the parameter we want to estimate. So this is the constant. This is not a random variable. And random variable is D. But you take expectation, that expectation result will no longer be random variable. It is a fixed value. So this is the constant. This is the constant. Take the expectation. Expectation of a constant is the same constant. So this is equal to this, right? Okay, so we have this. And then this is the constant. This is the constant. For expectation, this is the constant. This is the constant. This is the constant. This is the random variable. So you take the expectation of the whole thing. We can simply take the expectation for this random variable. So we put this E into here, E of D here and here. So E of D minus E of D, this is 0. So you get So you don't have this term. You only have those two terms. All right, those two terms are very important. So the mean square error of the estimator is equal to, look at this, d minus expectation of d. d minus the mean of this random variable. So this is like variance. So this term is the variance of the estimator, this term. And this term, what is this? This is the bias. So this is expectation minus the expectation of your estimator minus the original parameter. This is the bias. This is the square of the bias. So you always remember that the mean square error is equal to the variance of your estimator plus the square of your bias of the estimator. This is always true. So I want you to remember this. Mean square error is always equal to this, which is denoted as this. Variance of d plus b theta of d squared. This. Okay? And very important, when we go into this concept can also be applied to deep learning. The deep learning, your estimator is this, right? It's the same. It's the same. So for deep learning, we still need this kind of concept. So let me say it again. Mean square error is equal to the variance of the estimator plus square of the bias of the estimator, which is this. Okay. So basically, what does this mean? It means this. You see, we have every time if we design our estimator, every time we apply our estimator based on the data, don't forget, our data is a random variable because our data contains noise. So data is a noise, is a random variable. So every time we use those random variables and design our estimator to estimate the parameter we want to estimate, every time we will get different results. Sometimes here, sometimes here, sometimes here. So this is our result. This is the result. Okay. And so the real one is here. The real one is this. So if the variation of our estimation result is like this, the mean of our variation, the mean of, say, suppose we do estimation 1, 2, 3, 4, 5, 6, 7. We do our estimation 7 times. Every time we will have different results. But it will vary within this range. The mean of this range, of this estimated result is this E of t, which is E of t here. And the real one, the real parameter actually is here. So the mean of your estimation, the difference between your estimate, the difference between the mean of your estimation and the real parameter, it is called bias. This is called bias. And the variance is the variation, the range of variation. This is your variance. This is how we do it. So the mean square error is actually the variance plus square of this bias. This is, for any estimator, it's always like this. This is statistical property. Okay? Okay. All right, so we have, look at this. So you got, all right. Now you are familiar with this. G of x, we can ignore this term because this is constant. We have this. Now, a very interesting question. What if, see, I is equal to 1 to capital K. Oh. Well, okay, forget it. Then next week we'll go through those theoretical parts, okay? Those theoretical parts are not directly related to our exam, but actually you have to know this. As a graduate student, most of you are graduate students. As a graduate student, you should know this statistical part. All right, okay, see you next week. Please go home, try those data, okay?